Alright, so today we're going to look at a material and energy balance problem. This is our problem that we are given, and this paragraph here just describes the situation that we're trying to simulate, and then the table down here gives us the values of different parameters that we may find useful. So this problem is a CSTR problem. So what does CSTR mean? So CSTR stands for continuously stirred tank reactor. So what does that mean? So that means that we're going to have a tank, right? So we're going to have some sort of tank. We're going to have something inside the tank, and it's a reactor, which means there's going to be a reaction that occurs inside the tank. And if you look down here, we see that it's an exothermic, irreversible, first-order reaction modeled by the basic formula A goes to B. So we can put that inside here. So A is going to go to B. All right, so then the other key part of this is that it is a continuously stirred tank reactor. So we're going to draw a little stirring device in here. So that's a stirring device. So what does it mean for something to be stirred? So also for this tank reactor, we're going to have some flow going in and some sort of flow coming out. So what does it mean for something to be continuously stirred or perfectly mixed, or some term like that? So it uses continuously stirred here, but if you see terms like perfectly mixed, well stirred, perfectly stirred, stuff like that, it all means the same thing. So to understand what that means, let's first think about what happens if this isn't continuously mixed. So we'll have some amount of A coming in. And so it could be at any concentration, any temperature. And those concentrations and temperatures can be different from the concentration and temperature of A already inside the reactor and of that going out. So we have A coming in at a certain temperature and concentration, and let's say those are both higher than our initial concentration and temperature inside here. They don't have to be, but this is just an example. So that means that right here, right where it's coming in, is going to have, if this isn't well stirred, the area right over here is going to have a higher concentration and temperature, whereas the area farthest away from where that's coming in is going to have a lower concentration and temperature, and there's going to be kind of like a gradient across our tank of concentration and temperature. And that's going to be really hard to simulate because that means that the stuff that's coming out depends on where that outlet is in relation to the gradient and stuff like that, and that's just going to be really hard to simulate. So if you stir it up, that means that the concentration and temperature inside the tank are going to be constant. Or not constant, but consistent throughout the entire tank. They both still change as more A, more heat, whatever is added or taken away or whatever. So they're not constant in terms of time. They will change over time, but it's constant throughout the entire solution inside of the tank. And that means that the concentration and temperature of whatever's inside the tank is going to be equivalent to the concentration and temperature of the stuff that is flowing out of the tank, which is going to be a lot easier for us to simulate and will still give us some pretty useful values. Alright, so now that we know kind of what we're looking at, so we keep reading the problem, and it says that we want to simulate the effect of change in coolant temperature. So that means we're going to need a coolant of some sort. And this makes sense because, it tells us in the problem that we have an exothermic reaction. So an exothermic reaction is going to release heat as it reacts, most likely changing, most likely causing the temperature to increase. And, we don't want, in a real life situation, you're not going to want something to just be continuously increasing in temperature without any sort of, control over that, because it's how fires and explosions and, stuff like that happens. So we're going to want some way to kind of, regulate the temperature. And so for this problem, we're going to use a coolant to do that. And So basically means we just put this tank that has a reactor in it inside of another tank that has some sort of coolant inside of it. You know, something that's going to absorb the heat of this reaction and, you know, regulate the temperature a little bit. And also we're going to have this means that we're going to have some temperature going in and some sort of temperature coming out. All right. So next, let's kind of look at some of the variables that we have been given. Or, well, maybe first we should figure out what we're trying to simulate. So it says that the two state variables of the ordinary differential equations, so those are the differential equations that I'm going to show you how to derive, are the concentration of A, which is our reactant, and the reactor temperature. So that basically means we're looking for two things. We're going to want a change in concentration of A with respect to time, and we're going to want change in temperature with respect to time. So those are the two things we're looking for, and this is where material and energy balances come in. So this first one up here is going to be found from a material balance, and then the change in temperature with respect to time is going to be found using an energy balance. All right. So then, let's look at some of the values that it gives us. So, first thing it gives us is Q, and Q has units of liters per million, so that's, you know, a flow rate. So, it only gives us one flow rate in this problem, so we can assume that, you know, the flow rate going in and the flow rate going out are equivalent, and that they are 100 liters per minute. So, flow is continuous, which means that volume is going to be constant. And you can see down here, it also gives us a volume of 100 liters. So, you know, volume in there. All right, so then next thing it gives us is CAI, and that might be a little bit confusing, because you might be like, well, is that the concentration of A going in? Is that the concentration of A inside the tank? Is that the concentration of A, you know, initially? And we can see that down here, it gives us some initial conditions. That's what parentheses 0 means. So that means, you know, the temperature of the coolant at time 0, concentration of A at time 0. So that means this isn't concentration initial. And, you know, temperature of, you know, inside the reaction. So it's going to have a temperature, and this will have that temperature. So we'll change that to be like T out. Alright, actually I'll write that in so it doesn't get confused with T initial. Alright, so that means that this is going to be the concentration of A going in. So we can write that up here. That's the concentration of A going in. And then we have the density. So there's only one density it gives us, so we can assume that the reaction that occurs within this thing isn't going to change the density of anything. We're going to have a negligible change in the density, so we can say that the density overall is, you know, 1,000 grams per liter. All right, so then it gives us C, and so C here is going to be a heat capacity, and you can tell this by the units, joules per grams Kelvin. So that's going to be the heat capacity. Then we're given a negative delta H. So delta H is going to be the heat of the reaction, and it's negative because it's an exothermic reaction. So exothermic reaction has a negative heat of reaction, and they've just put the negative on this side so we can you know, divide that negative sign across, and we'll have that the positive heat of reaction is equal to negative 5 times 10 to the 4th. All right, so these next two values, they deal with the Arrhenius equation. So I have the Arrhenius equation pulled up for us here for reference. So this is what the Arrhenius equation is. Right. this in a different way. So the radius equation k is equal to a times e to the negative e over rt. So k is our rate constant, and a is our factor, and in our problem they've actually given a as k naught, just a different variable name, but it's the same thing. So we're going to replace that a there with the k naught. So we have k naught, and then we'll have the temperatures from over here, and then E over R is given to us, already divided out. So maybe a better way to write this would be like k is equal to k0 e to the negative, and then it's like e minus r, like as a quantity, because it's already given to us over t. So we have that. So we'll be able to calculate our rate constant. You're always left as a rate constant, so don't forget. So that's for the rate of our reaction. And then from this, we'll be able to use that rate constant for our first order reaction. So since it's a first order reaction, first order reaction, that means that our overall rate of reaction is going to be equal to rate constant times the concentration of A. So then it also gives us UA, and that is a heat transfer coefficient. So that means that the transfer of heat, between the tank and the coolant can be modeled by that UA. So that means so that would be the heat transfer is the UA value times the differences in temperature. So like that. All right, so the next thing that we're going to want to do is look at writing these differential equations that we can use. So first one is going to be based off of a material balance. So what do we think when we think material balance? So we think that, the mass that is accumulated within a system, so that would be the amount of A, so we're going to be looking at the material balance of A. So the amount of A inside this tank is going to be equal to the amount of A that goes in, so that's the amount of A that's coming from this incoming stream, and then minus the amount of A that goes out, so that's going to be the amount of A in this outgoing stream, and then minus the amount consumed. So this reaction is consuming A because it's taking A, it's turning it into some product B. So that reaction is going to consume A. All right, so now let's get this in terms of things that we know. So the mass, accumulated, so that's where we're going to have this. So we're going to have, the change in concentration of A over the change in time. So we're going to have this material balance as a relation of time. So right now, so we're going to want to look and make sure that all of our units work out, and that's the easiest way to kind of think through this problem. So we're going to, for this one, we're going to want to get things in units of moles, because that's amount per minute, which is time. So we're going to want every term in this equation to be moles per minute. So right now, for this, we've got a concentration, which is moles per liter, and then per time. So we have that extra liter in there, so we're going to need to multiply by volume to give us that liter. Right, because then we have moles per liter per time times liter. out, we get moles per minute, right? So that's kind of how we're going to think through all of these. So now let's look at the mass going in. So what do we know about the stuff that's going in? We know the concentration, we know the rate. So we've got the rate, which is in liters per minute. So I'll write that up here. So liters per minute. So we got the minute on the bottom that we're looking for. Let's also look at the concentration. So we can multiply this by the concentration, which is moles per liter. So that's concentration that goes in, which is moles per liter. Liters cancel out, we get moles per minute. That's what we're looking for. I just dropped my pen. All right. Anyway, so we're good on that term. Now let's go from that amount going out. So that's going to be a very similar deal. We've got this amount going out. I also forgot to label. We know the concentration going out because that's going to be the same as the concentration inside the tank. So similar deal here. We know the Q going out, and we know the concentration of A, and those units are the same as that, so I'm not going to write that again. So this, now let's look at the amount consumed. So for that, we're going to use these equations that we had before, these two. So we, right, so we know the rate. And this rate is, K times CA, which I'm just going to write as K times CA. So I'll write that over here. So K times CA. So what units are that going to have? So K is going to have the units of K naught up here, which is 1 over minutes. So 1 over minutes, that's our time piece. Times concentration, which is going to be moles per liter. So moles per liter. So we need to get rid of moles, so we're going to multiply that by volume. Or we need to get rid of liters, so we're going to multiply that by volume. So we get rid of liters, and then we've got moles per minute. So yeah, that's the equation that we're going to want to use. We can rearrange it a little bit so we can get this term on one side by itself. To do that, we just divide out V, and then we can also factor out this Q here. So I'm going to do that all in one step, so I don't have to write as much. So I'm going to have the change in concentration of A with respect to time. It's going to be equal to, so we're going to factor out this Q, and then we're going to divide out the V. So Q, rate going in over volume times concentration of A going in minus concentration of A inside the tank and going out minus, so then the volumes will cancel over here, so then we'll just have minus K times concentration of A. So that's our material balance equation that we're going to want to use. Alright, so the next thing that we're going to want to look at is the energy balance part of this. So we're going to want to get to the change in temperature with respect to the change in time, and we're going to do that using an energy balance. So when you think about an energy balance, you have that the change in energy is equal to the energy that goes in minus the energy that goes out. Right, so it's similar to the mass balance, but there's nothing consumed. Energy doesn't really get consumed. So first we're going to look at this change in energy portion on this side, and that's where we're going to have this. So we're going to have change in temperature with respect to time. So that's what we're going to want to solve for eventually. So again, let's pay attention to our units. So for this part, we're going to want to get units of joules per minute. So joules is energy with relation to time. So joules per minute right now, with this part, we've got Kelvin per minute. So I'm going to deal with that. So we're going to get rid of the Kelvin. Something that has Kelvin on the bottom is the heat capacity. So multiply by the heat capacity, which is joules per gram Kelvin. So the Kelvins cancel. We get the joules on top that we're looking for. Now we just got to deal with the grams. So something that has grams in it, really the only thing that has grams in it is going to be this density here. So we'll multiply it by the density, which is grams per liter. But then we have liters that we need to cancel out, and we can cancel those out with the volume. Times liters cancel out, we get joules per minute, which is what we're looking for. All right. So next, we're going to want to look at, like the change in energy here. So, one way the energy is going to change is going to be like a change in enthalpy. So we can just write that as like enthalpy in minus enthalpy out. And overall, that is a change in enthalpy. And the other way that the energy is going to change is going to be by this heat transfer that we've got. So you just put that on the end. So we have UA times temperature of inside the tank minus temperature of coolant. And let's just check the units there and make sure everything works out. So we have UA is joules per minute times Kelvin. Temperature minus temperature is going to be Kelvin. And we get joules per minute. So that all works out. All right, so now let's look more closely at this change in enthalpy. So we've got change in temperature, let's write this down. So I'm just copying this part down. All right, so how does the enthalpy change? So the enthalpy is going to change in our situation by two factors. One is going to be the change in temperature, and the one is going to be the energy released by this reaction, or enthalpy released by this reaction. So let's deal with the change in temperature, inside there first. So we've got, so we're going to want to have a change in temperature. So temperature that comes in minus the temperature, inside the reactor. So that's T, and then, so then, I didn't write it over here, but TI, so that's TI versus TN, because why not? And then temperature that comes out is going to be the same as temperature inside, so that'll be over there. So that's going to be the change in temperature. Obviously, we can't just have that because we're, that's just going to be units of Kelvin, and that's not what we're looking for. So if units of Kelvin, we need to cancel out units of Kelvin. So again, we're going to use the heat capacity because that has Kelvin on the bottom. So times the heat capacity, which is joules per gram Kelvin. So Kelvins cancel out. We've got joules per gram. Again, gram, the only thing we can do with that is this density. So density is grams per liter. So then we have liters to cancel out. So you might think we were going to use the volume again like we did over here, but that will just get us to joules. We're looking for joules per minute, and if you notice, the Q that we have actually has liters, units of liters per minute, so that'll, do that for us. So, liters per minute, so then we get the liters gone, and then we got the minute, time of minutes that we want. All right, so that's good for that term. So then the other way that this is going to change in enthalpy is going to be our heat of reaction. So we can put that in there. And again, as I said, we're going to divide this negative sign out. So we're going to have the positive enthalpy of reaction is going to be negative of this value. So I'm just going to write this with a plus sign because of that. We'll just be careful when we're going through the coding to do this to make sure there are negative signs and everything works out. But anyway, the heat of reaction, which is in joules per mole. So we got the joules, we got mole dependency that we don't want. So we're gonna, I this is like the heat of reaction, so we're gonna want to multiply this by like the amount that reacted. So how much reacted, that's going to depend on the concentration of A, so that, which is moles per liter, and we'll get rid of that mole dependency. So times concentration of A, which is moles per liter. Got a liter on the bottom, so we can cancel that out with the volume. And then we're going to need a time dependency, which for this, we're going to use this rate constant, which is, relating to the rate of the reaction. So this rate constant, because it has units of 1 over minute, so times K, so then times 1 over minute. So we get the joule per minute that we want, and then we just bring this term down here to be plus UA times T minus C. All right, so there's, the main equation, but let's, rearrange it a little bit to get this by itself on one side. So we've got change in temperature with respect to time is going to be equal to, so we'll have T n minus temperature over, all right, so then C's will cancel here, densities will cancel here. We're going to get Q over volume, and then we'll have, so plus the heat of reaction, so concentration, volumes are going to cancel, K will not, over heat capacity times density, and then we just have this third term over here, which nothing's going to cancel there, so we're just going to have UA temperature minus temperature performance over heat capacity times density times volume. So there's our equation, box that in. All right, so there are the differential equations that we're going to use to simulate this problem. So I'll show you how to simulate it in the next video. See you then.